screen.
Sure. Okay, we're now live for our structural modeling video conference for August 2016. We have Kevin Dye will be presenting part-whole relations, and we have a few people online now. Then we'll have maybe joined by other people as we go forward. So I'll let Kevin introduce himself, and with that, I'll turn it over to Kevin.
Okay, so this is a specialization of interpretive structural modeling focused on part-whole hierarchies, and it's looking at part-whole relationships through 5 or 6 disciplinary lenses which don't talk much to each other. The first part of the presentation is going to cover mereology, which is mathematical logic, and that is the most formalized and well-developed approach to part-whole relations. And people that do object-oriented systems, for example, are looking to mereology to try to understand how to handle aggregation and composition. And they're surprisingly poor at accommodating math that's been developed for over half a century. Meronymy is the linguistic view of part-whole relationships. Partonymies is the psychological and cognitive science view of relations. Functions is an engineering view of part-whole relations, part-whole being functions and subfunctions. Aggregation and composites are from object-oriented or unified modeling language views. And so let's start. The part of relation is one of 2 major ways people tend to think. They think in terms of comparisons, which is ISA types of relationships, and they think in terms of parts, which involve more functional relationships in general. Meros is the root of the term mereology and meronymy. The basic reason we exploit part-whole relationships in systems science is because it reduces complexity by treating many objects as one object. That's very straightforward, but we kind of forget what is the function of calling a collection of objects by one name. The value of it is in terms of complexity reduction, which is a theme of the Simpsons work. Now, mereology really got going in the late 1800s as an alternative to set theory. The disconsternation with set theory is that it had this fictitious idea of the null set or the empty set, and so they wanted to try to have a more elegant approach than set theory. It never really got accepted as an alternative to set theory, but it's possible. For example, we could rewrite the mathematics behind basic structural modeling in terms of mereology instead of in terms of set theory like Warfield did. That's not what this presentation's about, but it's just an interesting aspect of it. Now, it's a collection of different approaches because there's not a single agreement on what mereology is. So there's a number of different formalizations of it depending on which primitive you start with, what axioms you choose to exploit as the foundations, and even which type of logic, for example, modal logic or predicate calculus. So it's not even, I wouldn't say a family, it's just a loose collection of formal systems. So disciplinary views, is what I mentioned on the first page. One I didn't mention was ontologies. There's a lot of work in ontologies in the software world these days, and origins of work on ontologies is from a number of different realms: philosophy, phenomenology, domain engineering, conceptual modeling, computer science, and then, of course, systems science. So this is the outline of the Mereology pages. Each page is pretty straightforward. We'll just first look at the history of how this came about in philosophy and then found its way into math. Parthood, the primitive that we're going to start with here is parthood as a partial order. There are other approaches that start with proper parthood. So we'll go over the axioms of 4 different axiomatizations of Mereology. The first one is called M, or core Mereology. We'll give examples of those. Then we'll look at proper parthood, which is a strict partial order. And these have interpretations in Joe's outline, the AMEI, his coding of that is trying to generalize the relationships of reflexivity, symmetry, and transitivity. Then, what Joe has outlined covers partial order, and partial orders are very general. Parthood is one type of thing that can be a partial order, but to have something that works with kind of the common sense of what a part and a whole would be, you need additional rules. One type of rule is called supplementation, which just means that you got to have more than one part in a whole. And there's a couple different versions of that. And to make the leap to the general extensional Mereology, you add a compositional principle that you can always form a fusion of parts to create new wholes. And an interesting aspect of this is when you add these additional axioms, it turns out that Mereology can be a substitute for Boolean algebra, the general extensional Mereology. So this there are discussions of part-whole ideas that go back to Aristotle and Leibniz, but people generally consider Brentano as a primary influence in the late 1800s. And one of his students was Lesniewski, a Pole. And Lesniewski and Tarski and one other person formed the Moscow Trio, I think they referred to it as, and they made a lot of advances in set theory and substitutes for set theory, experimenting with different logical systems to carry it out. Quine was aware of that work. Quine, very influenced by William James, the pragmatist, and he was a professor of Nelson Goodman. Nelson Goodman did not know about Lesniewski's work initially and was looking at an alternative to Carnap's work called the Aufbau, which is his development of set theory. So Goodman was rejecting set theory. He didn't believe that you should have abstract things like a null set. So he wanted something very tangible. in the math that was closer to common sense, and his position is often referred to as nominalism. Some big names, of course, in math: Whitehead and Russell, the authors of the Principia Mathematica. They had an attempt to redefine set theory, or redefine all of mathematics in terms of logic. It was eventually a failed program because of Gödel's theorem. But Whitehead was a professor of Henry Leonard, and Nelson Goodman and Leonard composed this new field of mereology called the calculus of individuals, and then it was realized by Tarski that they basically had done the same thing as Laniusky. Today's presentation is based on Varzy's, he's in the lower right, Varzy's articulation of mereology. He's kind of become an accepted standard bearer. A few other names that, just to tell you, to give you an idea of the realm of people here. Goodman was a professor of Noam Chomsky, the noted linguist, and Hilary Putnam, the noted American pragmatist. And they were both influential on Jerry Fodor, who's a cognitive scientist and language guy. This is kind of a family tree. You'll notice right in the center is the pragmatist Charles Saunders Peirce. A few other names to point out would be von Bertalanffy and Bunge. Bunge will revisit a lot more when we get into causal modeling. You'll notice in the bottom, under the AI bubble, is John Sowa. And people we just talked about are mostly under the Frege box: Russell, Quine, Goodman. And this is just another person's opinion of the family tree. So one way to start a mereological mereology as a formal system is to begin with parthood as a partial order, being reflexive, transitive, and antisymmetric. So verbally, everything is considered to be a part of itself. Any part of a thing is itself part of that thing, and two distinct things cannot be part of each other. I was wondering, Joe, about this with respect to the AMEI. When we talk about other people's systems, that includes antisymmetry. That doesn't really have a slot in the labeling system, does it? You with me, Joe? Oh, Joe's muted.
So I just turned on my microphone. So antisymmetry has an if statement in it.
Right.
So in the activity of structural modeling, where you are using two things, you're using the empirical data. You go get some data, you bring that in, and then you use the logic to determine which is the next highest value empirical data point to get. We are now focusing on the logical properties that do not have an if statement, because an if statement in that logical property means you have to go get more data. If it's this, then it's that, right? Or it's one or the other, but you don't know, right?
Right.
So at this point, that's exactly the reason that we don't use antisymmetry, and antisymmetry itself is composed of two more primitive logical properties. It's either going to be symmetric or it's going to be antisymmetric, right? One or the other in the final analysis. It's not going to be both at the same time.
Right.
Does that make sense?
Yep. Yeah, I just wanted to have that clarified.
So we're working with them. That's why in the AMEI we don't have anti-symmetry, because essentially we want to stick with the primitives right now.
Right. So right now this is an axiomatization of ground mereology, and it doesn't quite fit in our framework. But you'll see the next one, the next axiomatization it will. So this is just a formal statement in the math, and I have to apologize. All the Greek and math symbols got scrambled when I converted this to PDF, and I did not notice that that had happened until after it was sent out. So there's a new version that Joe's going to put up just in a PowerPoint mode. So an alternative axiomatization is proper parthood, which is a strict partial order, and this is irreflexive, asymmetric, and transitive, which is in the AMEI is IAT 221. So, for example, if Spain is a part of EU, since Spain is part of the EU and they are different entities. But just having those three properties, which was the focus of Warfield and development of interpretive structural modeling and basic structural modeling, we need a few more axioms to for our system to behave like a part-whole relationship. That was never done by Warfield, and I'm pretty sure it's not been done by anyone that's done new versions of interpretive structural modeling algorithms. So this is new stuff. So there are many ways to add axioms to create mereology as a formal system. One is called weak supplementation. Just means that a whole needs to have more than one part. It's defined in terms of overlap. And it means that if you have parts in a whole, there has to be something that doesn't overlap each other. In other words, they have to be distinct. So since Spain is a proper part of the EU, and EU has other parts that are disjoint of Spain, that's a proper part-whole relationship. So when you add weak supplementation, it's referred to as minimal mereology. And it turns out that supplementation, when you go through the logic, actually implies antisymmetry. So you can redefine your axiomatic system without antisymmetry. You can start with supplementation and transitivity, and that gives you another formal system. So we can drop antisymmetry. So there's a stronger way of expressing supplementation, which is to say, if a whole has a part, there's also got to be at least a remainder beyond that part. That's a stronger statement of supplementation. So, for example, Spain is not part of Africa. There's a part of Spain that is not part of Africa. So, little logical subtlety there. So when you add that stronger sense of supplementation, you have the system called extensional mereology. It's called extensional because of a theorem that can be derived from that, which is that no composite objects with the same proper parts can be distinguished, and there's other ways that property is expressed. So, for example, the territory of the Community of Madrid is the same as that of the Province of Madrid because both territories are composed of the same proper parts, that is, by the same municipalities. This is a highly debated aspect of mereological systems, and so there is even more axiomatization. So we've covered the first three on the highlighted by the bottom, and we're going to cover one more because these three are not decidable and cannot be a substitute for set theory or Boolean algebra, and it's felt that those properties would be valuable. So we're going to go to one more, jump up to GEM, the general extensional mereology, and that's by adding a composition principle. Any two objects have a sum, and the formal statements of that are below. This is the fusion also called the fusion axiom, and this is very debated as well because the classic example is my hand and Napoleon's foot can form a new whole, but does it make any sense because his foot doesn't exist anymore, it has nothing to do with me, and it's in another country. However, that is what general extensional mereology implies. So what we covered was the partial order, considered ground mereology. If you add weak supplementation, you get a minimal mereology. If you add strong supplementation and therefore extensionality, you get the EM. And if you add the composition at the top there, or unrestricted fusion, you get general extensional mereology. And the Haas diagram at the right shows you that there's even more axiomatizations. This has been reworked in many different ways, so we're not going to go over that. This is a little formal. Tarski, who was a member of the Moscow trio, recognized that what had been developed as mereology basically could stand in as a Boolean algebra if you get rid of the zero element. That's why I said at the beginning that we could rewrite the mathematics of basic structural modeling in terms of mereology. So, comparison to set theory, mereology is a calculus of individuals, whereas set theory is a calculus of classes. So, if we're going to right now, basic structural modeling is implemented according to set theory, and so we're using a calculus of classes to implement a calculus of individuals, and that's one of the reasons we have to add more axioms. And then there's subtle differences between part of relation and set inclusion and set membership, and this confusion went on for many decades, and it's a very subtle thing that I myself can't explain that well. So mereology doesn't distinguish between elementhood and subsethood, and it doesn't have abstract entities like sets, and it doesn't have an empty set. That's the primary difference with set theory. And if you're into the math, these are the I only went over three of the four of the properties that are dealt with in mereology. There's typically this 9 or a dozen of them, and here's the mapping between one of the axiomatizations of mereology and set theory. Now, here's the implications for what we have to do with basic structural modeling to be able to model parthood. We don't want ones down the diagonal, for example. For proper parthood, we don't want we don't want a whole or a part to be the same. So we want zeros on the diagonal if we were just representing proper parthood. For asymmetry, we never want to ask if B is a part of A if we've already asserted that A is part of B. However, if we did ask and it went in both ways, the way it would show up if we didn't ask is it would show up as a whole with one part. And that typically means that they're synonyms. But my feeling is to save, to economize on the number of questions you would ask in the inquiry, you should just never ask in both ways. Now, all the interpretive structural modeling algorithms right now do ask both ways because they're trying to detect cycles, which reduces, they condense the matrix when there are cycles. And so we don't want to do that with part-whole relationships. So in other words, we don't want to ask both. We don't want to ask about a relation both ways on the diagonal nor on the complement across the diagonal of the matrix. So these are additional rules in how the algorithm needs to work that happens prior to inquiry. The principle of supplementation, which implies that there's no holes with one part, we'd have to detect after the inquiry. So if it shows in the directed acyclic graph, for example, that A has only one part, then we need to ask a series of questions. If we already, for example, have completed the inquiry, and it turns out we have a whole with only one part, we want to see if it's really the same or not. Is it a synonym or not? So this is a proposed set of questions of how the inquiry might be generated. Is there another object we did not ask about, which may also be part of A? If not, are A and B identical, just different names for the same object? If not, can we identify another part we might not have generated in our starting set? And if we can't discern a difference and we can't find an additional part to add, then the matrix should be condensed. Now, right now, basic structural modeling and all the interpretive structural modeling algorithms I've seen condenses the matrix when you have a cycle. This would be a case of condensing the matrix if you only have one part. So that's a new way of matrix condensation that's not been introduced to the interpretive structural modeling algorithms before. Implications 4 and 5. So the principle of extension. If after inquiry there are two objects which are composed of the same parts, then we should check whether they can be distinguished, because extension says we don't have two different wholes made of the same parts. So we want to check, similar to what we previously did, whether those two wholes are synonyms. So this is an interesting addition to interpretive structural modeling. Usually when, for example, the way Christakis practices the overall structured what is now called structured dialogic design, or Warfield called interactive management, is that they would have an idea generation session. Usually nominal group technique was used for that. Then they'd have a clustering technique to find out things that are similar to each other, and then they would do interpretive structural modeling. Now this is a case where we're actually reversing that on a case-by-case basis when synonyms show up. And I've seen this happen many times. A cycle appears in an interpretive structural model, and it's really because people gave two different words to the same thing, and they didn't realize it even after the clustering session. And so this now is a clustering check that happens in the case that you have two different wholes made of the same parts. And then implication 5 concerns composition or fusion, which is just a stopping rule that the inquiry is not complete until you've considered all the pairwise combinations. And then implication 6 is from transitivity, and this is a new rule that would have to be added to how basic structural modeling works. Because if you've determined that B is in any way reachable from A, you don't want to ask the reverse. You don't want to ask if A is part of B, because that would violate asymmetry, and that's not inquiring about part-whole relationships. So for example, if a piston is part of an engine and thus part of a car, you don't want to ask, is the car part of a piston? So this is an additional rule, and it actually would speed up the inquiry time by reducing the number of questions. We would never ask to determine this cycle, because in our view of part wholes, we don't want such a cycle to exist. So I wanted to pause here because these are the major implications from mereology for how the structural modeling is handled. So maybe I can ask Joe, do you have any questions about what that would mean to the algorithm?
Well, I have a lot of questions, Kevin. You covered a tremendous amount of information in a very cohesive manner. And I think that there's my impression is kind of two things, and it's really what I had hoped that would happen. And my first impression is that with your experience in doing these events and actually working with people, doing the ISM events in different formats and different people, you have a lot of experience to show things that are problematic outside of just the mathematics and the logical approach. And then the second part is what I hear you saying is that the problematic approach, these problems are based in the translation from the natural language relationship, the linguistics, to the mathematics. And your idea and your example of the synonym, I think, is kind of the outstanding marker example there for me, where different groups of people have the same name for different things, and then that cycles through the mathematics and is treated as a cycle because you're not checking if it's the same thing.
Yeah.
So that's really great. I just
yeah, one guideline for that is, for example, when Christakis does the clustering session, his priority is to preserve any little nuance or distinction in what people say. So he has a bias to preserve everyone's statements, and this is suggesting that there should be you either have to consider a closer inspection of synonyms in the clusters, or you end up doing it on a case-by-case basis during the structural modeling.
Well, that's really an interesting approach, and one of the aspects of what you presented here, focusing on interpretive structural modeling and this part-whole relationship or mereology, a different type of mathematics that you would use to view this system, would be if you look at the way they do large-scale big data analysis, where you're going through and you're trying to discover patterns, discovering the meanings of words, you're discovering the semantics of different symbols by analyzing large sets of symbols. And one of the techniques they use there is essentially you do a map, you do a graph, and you show clustering. You show the semantic clustering of component meanings, right?
Yeah.
And so that's essentially what the way you determine semantic similarity in machine learning. So there's some very similar techniques that are available, pretty well developed now in machine learning, that you could use to pull out these similarities, and they're almost exactly what you're talking about. You just understand if these things all have the same attributes, then they're the same. Right? I don't care what you call it. If it, walks like a duck, quacks like a duck, it's a duck.
Yeah, the value of doing it interactively with people is often when you bring this to people's attention, they then will refine what their statement is or their label that they're giving their statement, which is something you wouldn't get from machine learning. So it's there's a fluidity in naming the parts when people are doing this. Now, this said, I should note that although Warfield identified the inclusion relationship and used that as a way to do part-whole structures, he only did a few examples of that, and they switched in, the Warfield and Christakis camp switched into a focus on influence diagrams very early, which is a type of causal relationship, and they never did much part-whole modeling at all. Christakis never did. And
yeah, so there's
it's so fundamental to systems modeling.
Yeah, the dimensionality paper, Warfield did a dimensionality paper by himself, and then Christakis and Warfield together authored another dimensionality paper, which deals with clusters and included in and so forth.
Yeah.
And it's it's really funny, I guess, that the point that you're talking about right now, and included in, I've been thinking about the last 2 weeks, the included in hierarchy that Mary and I developed really has fundamentally different relationships between the layers. And it depends exactly on whether or not you can have a part or a whole. And the thing that I've been thinking about, the relationship between the dimensionality aspects that were developed by Warfield and Christakis and what you just presented here, is the thing that got me thinking is, do I have to have more dimensions than my cluster? Right? So, because I see many examples where you don't have enough dimensions, or you use all the dimensions that are there when you translate up to creating clusters, and then then you select one of those clusters for your target. So translating down through that stack, the things that you talked about in neurology, whether or not are things that really apply to the analysis of that dimensionality stack. And I think there's some very fertile ground there for analyzing the foundations of the structural modeling and what that application is from natural language to the mathematics and back. Oh. And so that's the area that Mary and I called structural integration modeling, and we developed these tools so that you could actually start documenting and talking more precisely about these.
Right.
So hopefully that made some sense.
Yeah. Great. So I'll just continue. There are other formal systems of mereology that are that cover or start with axioms that are not the IAT 221 type in the AMEI. There's some of the words or the names of them are non-classical mereologies or non-well-founded mereologies or mereologies in which transitivity fails. So there's a whole, if we wanted to play out doing part-whole systems to cover other areas of the AMEI, there are maths to do that. Now that brings us to linguistics, which Joe just mentioned as an issue. The problem with intransitivity motivated the investigation of linguistics, which really didn't happen until like the 1960s and 70s, so almost a century behind the mathematical logic treatment of part wholes. One of the classic examples, if an arm is part of a musician and a musician is part of an orchestra, we don't say the arm is part of the orchestra. So it's that relationship is intransitive, but it's because it's mixing different notions of part and whole. In work by Winston and Chafin, they identified 6 major classes of part-whole relationships, and the feeling is that if you restrict the inquiry to be within one type or one class of relationship, that things do behave in a transitive way. That's somewhat debated, but the 6 are component or integral whole, and that would be the most common class that we would use in systems modeling. However, there are people that say that this is a so-called structured part-whole relationship, and that in general, structured part-whole relations cannot be said to be transitive. So this is kind of a messy area of the theory. The others member collection, like a tree or forest, portion, mass, slice, and pie, stuff, an object, steal in a bike, feature of an activity, paying is in shopping, or place and area, oasis and desert. So it happens that one of the big advances in part-whole theory is happening in geographic information systems, and Varzy's big book on the topic dealt with place-area as a type of part-whole relationships, a whole book just on that relationship for GIS systems. In language, there's about 40 terms that have more narrower definitions of part, and about 400 synonyms of the notion of part. But putting this together, this observation about language together with the observations of classes of part-whole relationships in language, I think an implication for interpretive structural modeling is you should never use the word part. If you want to find out about part-whole relationships, you should use more specific language than part. And so that may be one of the that's on the facilitation side. That's not about the math at all. That would be when you give instructions to people of how to answer, you wouldn't want to say, what are the parts of please name parts of the system. You'd want to say, name the subsystems, or name all the functions, something more specific. So in language, they identified part-whole relationships as a type of inclusion. That's not considered the way it is in mathematics, however. And there's a lot of confusion in in language because we confuse part-whole relationships with us in language with notions of perception, possession, ownership, attachment, attribution, and types of inclusion. Now, there are people that say that did a new taxonomy on the Winston and Chafin, and they say there's two major classes of part-whole relationships, structured and unstructured ones. And they say that the structured ones in general are not transitive. And the problem is down here in the list, one of the types of structured part-whole relationships that we're most concerned with in systems engineering is component complex relationships. And so there's a debate about whether, between people that think that that's not in general a transitive relation and people that say if you restrict the conversation to component complexes that it is. So it's kind of a messy area of this. And then underlying the taxonomy, Winston and Chafin identified three. Hold on, I have a truck going by. They identified three properties. Whether things are configurational, and that would be a property of most concern to system science. Whether they're homeomerous. In system science, we typically be working with heterogeneous parts, and whether things are separable or not. And in system science, we're mostly interested in things that are separable because of modularity. And that's how these properties line up with the different classes in language. A test for whether X is a meronym of Y is whether you can ask if X has a Y or Y is an X, and if it makes sense with both has-a and is-a, then it's a proper part-whole relation according to meronymy. So, for example, a wife has a husband, but a husband is a part of a wife. Doesn't make sense. Similarly, a sound has a pitch and a volume, but we don't say volume is part of a sound. Changing nappies is part of being a mother, but we don't say being a mother has changing nappies. But a book has pages, and a page is part of a book. That makes sense, and that's understood as a part-whole relation in language. Moving on to psychology, and this is really disconnected from the mathematical logic. But in general, psychology says this is one of the two main ways that we think in terms of part-whole or functional relationships and in terms of classes. They have rules about what form good part-whole relationships in psychology. One of the big ones is that there's a connection between the appearance of something and action with it. In other words, the appearance of an object often suggests or affords actions appropriate to it. In design theory is the notion of affordances, and that connection between appearance and function promotes the ability to inference about things. Now, what they find in psychology is people tend to think in only three levels deep. So this is quite at odds with big systems that have multiple levels. Our psychology is not really oriented to dealing with more than three levels. That's all I have to say about the psychology. Now, it's an implicit assumption that we're making here is that we're dealing with one thing at a time, and this is a classic statement of the separation of concerns by Dijkstra, a theorist in software engineering. He's basically saying when you're inquiring about a system that you're trying to build, deal with one aspect at a time. Deal with part-whole relationships, deal with class relationships, deal with causal relationships or method of functions between things. Do one thing at a time. And it turns out that's a good guidance for modeling, but you can't model a function with one thing. Functions are typically defined in terms in systems. Functions are typically defined in terms of both an object and an action, and so we kind of violate that principle of separation of concerns.
Kevin?
Yeah.
So we have about 15 more charts to go, and we have about 10 more minutes in the presentation time here. So would you like to think about finding a place to break off and ask some questions and then continue this up along next time?
Sure.
Okay. Sounds good. So we've got about 4 more minutes to summarize, and then we can have about 5 minutes of questions, and then we'll be done.
Sure, that's fine. So people that work on functional modeling, which is more in the engineering and systems world, claim that mereology is not expressive enough to cover the notion of functions. And one of the reasons is it needs to deal with more than one aspect at a time. And without getting into the math, one of the solutions or advances on mereology that's come from systems science is that we need to talk about X as part of Y at time t. That you have to have the time dimension in defining part of relationships. That's something that comes out of left field compared to the mathematical logic. They don't deal with that at all. And so there's a whole branch of advancing mereology to address time, so-called endurance and perdurance, so static objects versus processes. So if you want to talk about processes and part-whole relationships of processes, which is mostly what you're modeling in many systems, you have to have even tighter mereology than we already talked about. Object-oriented systems have not, even though the idea of aggregation is fundamental to object-oriented systems, they modeled it for a long time as a HAZA attribute, which is referred to as the belonging fallacy, that it doesn't really work. And there's a lot of confusion in the literature, and you see the confusion even in the names of the part-whole relationship: aggregation, composition, assembly, containment, membership. And there's really not a good definition of how to do part-whole relationships in object-oriented systems, even in unified modeling language. And there's been proposals about how to improve that, and they haven't really been taken up. And so it's really up to the person using the system to apply their own notion of part-whole relationship. Why they didn't draw on mereology is kind of a mystery. This is one of the proposals of how to make object-oriented systems more or better at capturing part-whole relationships. I'll just give you examples. So the implicit way that people define an object, for example, or define relationships, is they would say the attribute name, like wife is Mary and husband is John, versus an explicit way, which would be to say, here's John, here's Mary, and there's a whole that's composed of a wife and a husband who are Mary and John. So that simple change makes the part-whole relationship obvious, and explicit. But for a lot of people that program object-oriented systems, they do it implicitly and end up hiding the part-whole relationships. Another simple thing to do is to explicitly name the parts. So instead of saying has a wheel, you say it has a part called a wheel. Instead of has an engine, it has a part called an engine.
That's a great insight into the object-oriented software part, and there's a big area where people are actually looking at that and how those relationships are expressed to reduce the complexity in software. So that's really an excellent point. I think that this is a good time to kind of take a break here and see if there's any major questions or comments. I just like to say that as far as the transitive property goes, I think that there's an area where we could make some improvements in the idea of scoping. So the transitivity, when you think about it, you think, oh, it has infinite scope. Anything within this group of objects, it's transitive across them all, right? But if you added the concept of scope to transitivity, you say, well, it only goes for 100 objects or 10 objects or 3 or something like that. I have 3 or more is by definition, but I think that there's some areas where it would be very helpful to have the concept of scope, so that you would limit the transitive property for how far it could travel out away from the specific object that it originates from. So, are there any more questions?
Well, I just wanted to say, I wanted to commend you, Kevin, for putting this in such a presentable way. I feel that the contents of this presentation could be the subject of a whole day's discussion in teasing the implications of any one of the slides and the comments that you made in a variety of different settings. And so while time is pressing right now, I'm not going to sort of start that process, but just say that I think the implications of what you have presented are profound, and in so many different domains, as just the last sort of minute on object-oriented programming would represent. So that's my comment. Questions, gosh. I wondered about, you talked about psychological, just 3 levels. I mean, if the reference is there in your piece, that would be good. The other question I have is, as you talked about the sort of Mereology not being part of the original sort of design of ISM, what sort of kind of modeling now would you be calling is it structural integrated modeling? I mean, is there now that you're talking about these issues, what kind of modeling would you call where you're going with this?
Well, the original outline of contextual transitive relationships by Warfield in the 70s, which he developed with Frank Harari, they identified about 60 types of relationships they thought would be useful for modeling things. And inclusion was their word for part-whole relationships. Now, what I've seen in the literature of interpretive structural modeling, it's really the people in India have taken that up and do part-whole modeling with interpretive structural modeling, but they don't use the math. So they actually have much less efficient systems.
Yeah, I think there's been a real disconnect along those lines, and I'm really encouraged by the work that you've done, Kevin, to help obviate what these problems are, and hopefully we'll be able to build the mathematical connections back. And I think that what we've seen, and just what we've done here in the last few months, is that there's a few of these categories in the AMEI which are very, very valuable because of their because of the availability of many well-defined mathematical approaches that can be used to efficiently solve them. And then other ones, other buckets and categories within the AMEI really are challenging because essentially there's really no mathematics, no standard mathematics available. So as you've pointed out, there's these other mathematics that could be used in those cases. So we're at our hour, and this has been very valuable. I think we should finish this next month, and I'll try to work with people that would like to also give a presentation. Peter, would really like to hear from you and your view is, maybe next month or month after that. And it's been a great session. So with that, is there any final types of information? All right then. Well, I think what I'm going to do is stop this broadcast, and we will try it again next month.
Very good, Joe. Thanks, everybody.
Thank you, Kevin.